Welcome back to Physics 151 online. We're now going to ask the question, having defined work and what it means and how to calculate it, why might we be interested in doing that? What's the point of defining this new quantity? And so we'll just review the definition and show how we can rewrite it in such a way that it pertains directly to characteristics of an object's motion. So the most general kind of definition that we can make of work, remember, is through the dot product F dot ds, so the force acting on the object as it's moving through a displacement, a differential displacement ds, and then we integrate that quantity over a path that starts at one position and ends at another position. So what we're going to do with this is substitute for both of the terms in the integrand. And first, using Newton's second law, if the F is understood as the total force, the net force acting on the object, we can replace F with the mass times the acceleration. And we write acceleration as dv dt in calculus notation. Then ds, being a displacement, a vector displacement, that's equal to the velocity, the instantaneous velocity of the object, times a time interval dt. And so if that looks a little bit unfamiliar, just remember that the definition of v is ds over dt. And so all we're doing is solving for the differential displacement ds and writing it as v dt. So now we see that the dt terms cancel in this expression. And what we've essentially done is we've changed the integral from one involving an integral over a distance or position to an integral over a changing velocity. The mass comes outside of the integrand, and now of course we're integrating over time because we replaced the position variable with the time variable. So now we have dv dt dot v itself. And time, of course, is one of the variables, and the velocity is the other variable. Now, what we can do is use the product rule for dot products to find another way of writing down the integrand. And this is one of those things where you kind of have to know where you're going before you do it in order to get the answer. It might not seem obvious why we would choose to do this, but just for the sake of argument, let's take the time derivative of the dot product v dot v. Which is really just v squared, but we'll just write it like this. And the way the product rule works for dot products is the same as it does when you take the derivative of any product, except the dot product, the order is important. So the first term is dv dt dot v, and that's the first term here, and then we add to it v dot dv dt. And remember that if we change the order of the two vectors in the dot product, we introduce a minus sign into it, so the order has to stay the way it was in the original expression. But what you notice is that the dot product is commutative. Actually, yeah, so what I said was wrong. The order does not matter in the dot product. So v dot dv dt is the same as dv dt dot v, right? So I had that wrong the first time. Because of that fact, then we can add these two terms together and just write them as twice dv dt dot v. And that's exactly what we have in the integrand. So if we solve for this term here, it's just 1/2 of what we have on the left-hand side, right? So dv dt dot v is half d by dt of v squared. V dot v is just v times the cosine of 0, or v squared itself. So substituting that into our original expression for the work from the top line, we get the mass times the integral from one time to another of half d by dt of v squared dt. And what you see now is that these dt's cancel out, leaving us with an expression where we've basically changed the variable from time to velocity. So we end up with dv squared as the integrand, and because of that, now the limits have to be the limits on the velocity. So whatever the velocity was at time t1, we'll call that v initial, and what it is at time t2, we'll call v final. And so this might look a little bit odd, but if instead of v squared it just said x, then you would know exactly how to handle this, right? Because the integral of dx is nothing more than x evaluated between the limits. So here what we have is 1/2 m times v squared, which was the quantity inside the differential, v squared evaluated between v initial and v final, and here we get half mv final squared minus half mv initial squared. So for the most general case, which would be a three-dimensional displacement and a force that perhaps could be changing in time, we now have the most general expression for the work done on an object as it starts at an initial speed, v initial, and then ends up at a final speed, v final. And so we can restate this result, and because this 1/2 mv final squared plays such an important role in this expression for the work, we give it its own symbol, and we define 1/2 mv squared as the kinetic energy. And this is also sometimes called the energy of motion, because it's an energy that's associated with the object's velocity, or in this case actually just the speed. Notice that kinetic energy is a scalar. It does not depend on direction. It's simply a number, and it must always be a positive quantity because the mass is positive and the speed squared is always a positive quantity as well. So what we say in words is that the net work that's done on an object is equal to its change in kinetic energy. And that, of course, being a net work, it's the work done by all the forces. And so this is the starting point for the application of energy methods in the study of mechanics. So let's do an example. Here's an example that is a little bit more complicated because it involves a changing force. But it's going to be simplified by having an object that moves simply along the x direction. So we've got a block with a certain mass initially at rest at the origin, and then it's acted upon by a net force given by this rather complicated expression on the graph, and we want to know what the final speed is when the block reaches 4 meters. So notice that this force is the x component of the force, so it's the component of the force acting along the x direction. So what do we do with this? Well, the work energy theorem says if we can find the net work that's done, and assuming this is the only force acting on the object, if we can just integrate this quantity from the initial position to the final position, we'll get the net work that's done, and that's equal to the change in kinetic energy. In this case, since the initial velocity was 0, the object started at rest, then that net work will simply equal 1/2 mv final squared. So let's just go ahead and solve that for what we want. The final speed will be square root of twice the net work over the mass. And now what's left is simply to calculate the net work, starting from x equals 0. And what we see in this graph is it's going to be easy to find the area under the curve if we break the graph up into 3 different regions. The force is constant from x equals 0 to x equals 2. Then it has a constant slope from x equals 2 to 3. And finally from 3 to 4, again it has a constant value. Remember too that work can be both positive or negative, so we have to keep that in mind. So this is a fairly straightforward calculation. The work done from 0 to 2 meters is just the force times the distance, so it's 2 newtons times 2 meters, or 4 joules. Now from 2 to 3, what we notice is that the force graph crosses the x-axis. It goes to 0 at x equals 2.5, and then it's symmetrical about that x value. So the work done between 2 and 2.5 is positive work. It would be the area of that triangle, but it's going to be canceled by the negative work done between x equals 2.5 and 3, because it's the same shape, but it's below the x-axis and therefore has a negative area. So the work done between 2 and 3 is 0. And between 3 and 4, the force again is constant, but it's negative. It's in the negative x direction. And so if we were to form the dot product between the force and the displacement, we would see a negative sign. So it's just 1 meter times negative 2 joules, or negative 2 meters, which gives negative 2 joules. So the net work done on this object as it moves from x equals 0 to x equals 4 is 2 joules. And therefore if we take that value and plug it into the expression for the final speed, we get 2 times 2 joules over 12 kilograms. And joules, a joule is a Newton meter, which is a kilogram meter squared per second squared. And so the kilograms drop out, and underneath the square root we get a meter squared per second squared, the square root of which is meters per second. And so this final speed, what's nice about it, we can check it. It's got a positive value, which being a square root, it definitely should have. And the value itself is not very fast, but then again, we notice that part of the force was positive and then part of the force was negative while the object was moving along this direction, and it started from rest, and so it didn't have any initial speed to start with. So the value at least is plausible. So that's a simple example of how to use the work energy theorem. And then the last thing I want to introduce today is one more term that's very closely related to work, and that is power. Power is defined as the rate at which work is done, and particularly if we want to understand machines that are invented for the purpose of doing work, one of the ways that we rate those machines or discuss their effectiveness is to talk about how much power they can supply. Not just how much work they can do, but how quickly they can do it. So power is defined as the rate of doing work, and the calculus expression therefore would be dW over dt, the work done per unit time. So as a result, we can quantify the unit of power in the SI system of units. Power is then just an energy in joules divided by a time in seconds, and in honor of the inventor of the steam engine back in the 18th century, we give that name watt for the unit for power. Be careful though, because you'll see that there's a little bit of a possible confusion since the abbreviation for the unit of power is W. So if we talk about power in watts, there'll be a symbol with a W used to indicate the unit, but that's not the same as work. So work is measured in joules, power is measured in watts. So just be very careful with the units. But there's also a slightly different common unit that we often use in quantifying power, because in our industrial society we use large amounts of electrical energy. And so if that energy were described in joules, we would have huge exponents, as you'll see in just a minute with my example that I'm going to do. And as a result of that, we sometimes quote work energies and power energies in these different units. So power sometimes is quoted in kilowatts instead of in watts, and therefore the energy unit or the unit for work would not be watt seconds, but would be kilowatt hours, because this electrical energy that is supplied by power plants is often consumed over long periods of times. So hours are often more relevant than seconds. So let's just see how this would work if we want to ask the question, how many joules of energy are required to run an appliance that draws 1.5 kilowatts for 24 hours? So we're going to express the energy in kilowatt hours. It would just be the product of the power times the time, right? Because if power is constant, then instead of writing this as a derivative, we can just write this as the amount of work done, delta W, over the amount of time it takes, delta T. So then the work done would be power times delta T, and as long as the power that's supplied is constant, this works. So delta W then would be 1.5 kilowatts times 24 hours. And if we want to use the standard units that electrical utility companies use, that would be 36 kilowatt hours. And that's perfectly fine, but let's just convert that to joules to see how this compares to the value in joules. So we need a conversion factor that'll take us between joules and kilowatts, and then we also need a conversion factor that'll take us between seconds and hours. So a kilowatt hour, let's see, a kilowatt would be 1,000 joules per second, because a watt is a joule per second. So 1,000 joules per second is the same as 1 kilowatt, and this will cause the kilowatt terms to cancel. And then we want to get rid of hours and replace them with seconds, and so we use the conversion factor 3,600 seconds per hour. And when we do this, of course, the units work out fine because we end up with an answer that's just going to be in joules, but you'll see that 36 kilowatt hours is equivalent to 1.3 times 100 million joules, right? So it would be 130 million joules. So rather than deal with such large numbers, if we were to use joules all the time for electrical energy, we often use kilowatt hours instead. So I hope this has been a useful introduction to the work energy theorem and to the concept of power. There's one more thing I want to do before I leave, and that is simply to show an alternate way of expressing power. And this is in terms of the object's motion. So what we first did was define power as the work done per unit time, but it should also then depend on the rate of the object's displacement. Since work involves force times displacement, we should be able to relate power to the rate of displacement, and another word for that is velocity. So remember that in one dimension, we just wrote down this equation in the example a minute ago, that the work done is equal to the x component of the force times delta x. For a constant force, we can do this. So that in this case, we divide both sides by delta t, and we can get the average power that's done when the object moves through a distance delta x. So delta w over delta t is the average power. Put a bar on top to indicate an average. So that's fx delta x over delta t, and delta x over delta t is the average velocity along the x direction. So we'll call this v sub x bar, where the bar again indicates an average value. So for average power, we can write this as the force along the x direction times the velocity along the x direction. Now what about instantaneous power? Well, for a one-dimensional situation, of course, we would want this to be a derivative, a dw dt, and what that would be then, instead of having an average velocity, we would indicate the instantaneous power as the force multiplied by the instantaneous velocity along the x direction. And of course that velocity could change, and so the power would change if the velocity changed. But this is the appropriate expression for a one-dimensional system for power. And you can see pretty easily how you would generalize this if you had a three-dimensional case where there was a force acting perhaps over not just the x direction but the x, y, and z direction, and then the velocity itself could have components along x, y, and z. So what you would have then for a three-dimensional case is just the sum of those three terms. So we would have fx vx plus fy vy plus fz vz. And a very compact way of writing that down is to use the dot product again. And so the power instantaneously for the most general three-dimensional case can be written as the dot product of force and velocity. That can be useful if we have information about forces and velocities in component notation. Okay, so that's the introduction, and I will see you in class.